Good morning, folks. Another late one today. My apologies. Simplest imaginable technical difficulty. I'm usually recording these things around midnight. And right around midnight last night, I reached for my stack of paper and I found these two pieces of paper, and that's it. And that wasn't going to cut it, of course, because we blow through about 7 pieces of paper per lecture. Um, and we're kind of ballpark almost paperless in my household. So turns out midnight, not a particularly useful time to go hunting for paper that almost non-existent in my house. So sorry about that, everyone. Recording this morning at the time that normally we would just be arriving to class right now. So I'm going to hope to get through this one quickly, get it uploaded, get it processed, and maybe be posted before what would be the end of class, I hope. Okay, so we've been talking about capillary electrophoresis. We've gotten a pretty nice picture of the separation mechanism. Electrophoresis, electroosmosis in a capillary. We've looked at, how do we get a sample injected? What kind of detectors do we use? We've even seen that with really high sensitivity detection like fluorescence, we can approach some stunning detection limits because the volumes are so small. So I'm going to, full disclosure, be extremely biased here because I spent most of my career working in CE. But I'm going to be biased here and I'm going to make a bold statement. And that bold statement is CE is awesome. I'm not going to go quite as far as to say it's the number one best separation technique for everything. In fact, it's not the number one best separation technique for everything, but it has some really amazing properties that we don't find in most chromatography methods that, for me, have been intriguing for my entire career. So let's point some of those out, right? So CE does not suffer from, it has no multi-path or eddy diffusion term in the Van Deemter equation, so no A term. It has no mass transfer term, or what we call the C term in the Van Deemter equation. And these are the properties that make peak efficiency, which I'll remind you we quantify via the number of theoretical plates, capital N. This is what makes the peak efficiency property of, the faster, the better. And that is a very unique property of CE that we don't find in any other chromatography. We have said that we make the, in traditional chromatography, we have said that we make the sacrifice. We let N get poorer. We let H get larger, if you want to think about it that way, by going faster because we can get a faster result and we can get good enough resolution from the kind of the compromised peak efficiency. But in CE, we don't have to make that compromise. In CE, we just go as fast as we can. And if we go as fast as we can, we get the best peak efficiency we possibly can. Here's another thing that I find extremely intriguing about this. I'm going to say extremely small sample volumes. So an extremely small sample volume, we're talking about on the order of 1 nanoliter. This is the volume that gets injected into the capillary. And the side effect of this, one of the things that makes this so powerful, besides just being cool in and of itself, right? If you have a sample limited system you want to study, this is a great way to do it because you're not going to use much of that sample. Besides just being cool in and of itself, this is the property that means that with high sensitivity detection, right, with a high sensitivity detection method like laser induced fluorescence is a really good example of this. We can approach it's pretty ambitious to say single molecule detection, but we can approach single molecule detection, right? We can start measuring dozens or hundreds of molecules uh, fairly straightforwardly. You can measure hundreds of molecules by this method. So that's incredible levels of sensitivity. And another reason I think it's so awesome, it's designed for molecules that are ionized in solution, right? Charged molecules with some acid-base chemistry. That means it is very well suited for studying biomolecules. Most of these are polar molecules because, of course, the molecule, um, because the solvent of biology is water, right? So acid-base chemistry is very, very popular here. Also, we can design some very fancy biological systems that they give us lots of insight into biology, but don't give us a lot of sample to work with. CE is great for that. So CE is awesome, but there is a but, right? Everything has a but. Um, so let's think about CE migration order, and we'll see what the but is here. So here's what we said. So let's imagine we're migrating in this direction. How will these things separate out? Well, the thing that's going fastest up front will be something small and positively charged. Something medium and positively charged will be in the middle here. Something large and positively charged will be back here. Going in the other direction, we'll have something large and negatively charged, something medium and negatively charged, something small and negatively charged. And here's the but. What's right in the middle? Well, right in the middle are all of our neutrals, and it doesn't matter what their size is. They have no charge. They can be little tiny things. They can be enormous things. They have no charge, and so we get no resolution of any neutrals. And this can be a big problem. There's a lot of interesting chemistry that doesn't involve the kind of acid-base chemistry that will put charges on these things. Or maybe it does, and we're not at the right pH range to see the charged constituent, so it remains neutral, right? We get no resolution of these neutrals, and that's a pretty big problem. So what I want to talk to you about in this half of the lecture today is a modification of the CE technique that gets a new fancy long name that was designed specifically in the mid 80s to fix this problem, to get resolution of neutrals in this format of CE. So this technique, this CE related technique, is called Micellar. I always say micellar, and I just realized for the first time in my career yesterday, there's no U in here. It's micellar. Micellar Electrokinetic Chromatography. So we are back to chromatography, now electrophoresis. We'll see how that works. So to put it simply, this is a CE separation conducted with a high concentration of surfactant as an additive to the background electrolyte, or the buffer that we use, comparable to the mobile phase in CE. So we add a high concentration of surfactant to the background electrolyte. By doing that, we get into this mode called micellar electrokinetic chromatography. So let's look at what a surfactant is, just for those who are not familiar. So a surfactant is essentially, there's a fancy word for this, an amphiphile, an amphiphilic molecule. So we think about hydrophobicity and hydrophilicity. Sometimes we call hydrophobicity, so water hating, we call it lipophilic, oil loving. So amphi means, broad range of, or everything, or wide spectrum of, and philic means, loving. So surfactant is a molecule that will happily dissolve in either oil or water conditions. And so here's a classic one, the most common one I would suggest in many, many, many analytical chemistry applications. Certainly the most common in micellar electrokinetic chromatography, or I should have given you this abbreviation sooner, MEKC. It's almost exclusively referred to by this acronym, not by this long name. Okay, so common surfactant for this is sodium dodecyl sulfate, or SDS. Here's what SDS looks like. It's a 12 carbon chain, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, connected to a sulfate like that. And if you look at the structure of this molecule, if anybody in class works with lipids in their research, maybe you work for Dr. Best, maybe you work for Dr. Calhoun, and you've done some lipid stuff. We do lipid stuff in my lab too. Um, Maybe you work for Dr. Campagna, right? I know they do some interesting lipidomics up there as well. You'll recognize this structure as being very similar to the structure of a biological lipid, and that is it has this tail. In this case, in SDS, this is a 12 carbon saturated tail. It is hydrophobic naturally, as all saturated hydrocarbons would be. And then it's got this head group, this polar. In fact, in this case, it's not just polar, it's fully charged, and that's going to become important. Head group. And of course, that makes, because this is polar and charged, that makes this hydrophilic. And they're connected together into one molecule that is itself amphiphilic. It likes both oil-like environments and aqueous-like environments. Okay, so for any molecule like this includes lipids that you might be studying in your research. It includes biological lipids, but it's true, of course, of these synthetic surfactants. For any molecule like this, there's a certain concentration above which, so we're going to say above a certain concentration, and this certain concentration is specific to the molecular structure of your surfactant, but that certain concentration is called the critical micelle concentration, right, or the CMC. So above some certain concentration called the CMC, these things form surfactants, form micelles in solution. And I can tell you that the CMC for SDS is about 8.2 millimolar. So if you're above a concentration of 8.2 millimolar as an additive in your background electrolyte with this SDS, you're going to get these micelle structures. Let's take a look at what those look like. So when a surfactant forms a micelle, what's happening is the lipid tails are aggregating, the hydrophobic tails are aggregating together. They want to interact with each other, not with the aqueous environment around them. So they come together like this. Of course, the polar head groups have no problem being out in the aqueous solution environment, so they're out here. All right, so here's our polar head. And here is our hydrophobic tail. And what you end up with is an environment in here that looks a lot like a stationary phase, like the solvent bonded to a stationary phase. It's not bonded to anything, but there's this high density of these hydrophobic tails that if you imagine you had a hydrophobic molecule, it could partition in here. And this would act like a phase, right? Like an actual phase separating partition mechanism like we see in chromatography all the time. So how does this give us separation of neutrals in our CE separation? Let's take a look. Let's imagine we're in the capillary. Let's imagine just one of these micelles. So I'm going to draw this pretty small. There it is, head groups around it. So one of these micelles. and we're going to have some field across which we're doing electrophoresis. So we plus voltage over here, minus voltage over here. Now, electroosmotic flow is happening in here, but I want to ignore that for a second, just in our heads. This will work with or without electroosmotic flow. But let's just imagine the electrophoresis component. What does this micelle want to do? Well, if it's SDS, we know that actually these head groups all have a negative charge. In fact, this makes a structure with a pretty decent density of negative charges. It's also pretty large in size, so that's, those two factors are going to work against each other. But the bottom line is it's going to feel an electrophoretic velocity, VEP, back in this direction. Remember, EOF is probably pushing everything this way, but at least its electrophoresis is pushing it back this way. That's because it's negatively charged, and there's our positive voltage. Okay, so we have more than one micelle in solution. In fact, they're everywhere. And they're not just everywhere, they keep entering the capillary because they are in those vial tubes in those buffer vials that are at the entrance and exit of the capillary. So here's my very hastily drawn several micelles. And you can imagine lots of these things. We're at millimolar concentration. This is not nearly every micelle that would be in this picture. Okay, so what does that mean? Well, if you imagine you have, let's just think of two neutrals. So here's a little one and here's a big one. Size actually doesn't matter as much here, but I'm just going to use size as a way for us to think about two different molecules, right? These two different neutrals, they're different structures. They have different affinity for being dissolved in that phase, right? So you can imagine one of them may partition in. So let's just label this. This is partitioning. Partitioning into the micelle. And once it's done that, this neutral now has the electrophoretic velocity of this micelle, right? It's going to get carried along with it. Eventually, it's going to enter some space where the local concentration of this thing is very low. And then we know Fick's law of diffusion says this thing's going to leave, right? It's going to partition out. So eventually, it will partition out. Right, so partitioning out of the micelle, this neutral, and it ends up over here. And if it had higher affinity than this thing did, then it spent a lot of time partitioned in, this thing didn't partition in. And now we end up with this neutral here, right? This is the location in the capillary of this neutral. This thing didn't do any partitioning. It also doesn't have any electrophoretic velocity because it's neutral. It's now over here. These two things have ended up in two different places in space. They've separated. The short story here is that there will be partitioning competition between molecules for this lipophilic area inside the micelle. And when they partition in, they will take on the electrophoretic velocity of the micelle itself. The micelle will act as we have a term for this, the micelle is a pseudo stationary phase. Why a pseudo-stationary phase? Well, for starters, it's not stationary, right? It moves. That's actually a key part of this mechanism. If it doesn't move, if it's stationary just like the neutrals, these things can partition back and forth all day, but they're all just going to hang out together in the same region of space. So it is not stationary, but we can think about it like a stationary phase because as soon as this thing partitions out and one micelle moves along, there are so many micelles, there's a new one to come in and take its place. So you can always imagine some constant distribution of micelles throughout this capillary. Even though each individual micelle is moving, there's a constant flow in from one side of the capillary, constant flow out. So there's always a micelle to take its place. So there's some uniform density of micelles throughout this thing, and therefore they act like a stationary phase would. Just a couple more points to make on this, and then we will be done talking about MEKC. This brings us back to, this reintroduces phase partitioning, which is not something that we talked about in CE. In fact, we said it's one of the cool things about CE, right? There's no phase partitioning, and therefore there's no C term. This does have phase partitioning, and so the C term is back, my friends. So nothing comes for free. That's the price you're going to pay. You're going to get less efficient separations here, less efficient peaks, because we have a C term to consider again. The last thing I will tell you about MEKC, and then we will move on to another topic, is that there's a wide variety of surfactants available. A wide variety of surfactants. MEKC is actually a really popular tool um, for chiral separations. And we get those chiral separations by selecting a surfactant that has some chiral property, and therefore, if you have chirality in these micelle tails, you're going to get a preferential interaction of one half of an enantiomeric pair than the other, based on its preferential interaction with that chirality. Okay, this is MEKC. We're going to talk next about another limiting factor of CE that leads us to the topic of gel electrophoresis.